I am Maria Isfan, and I am a PhD student at University of Bucharest in Romania, and also a member of the Space Q group led by Laurențiu Caramete and part of the CU L2A. And today I will talk about our results concerning quantum neural networks for LISA low latency data analysis. So why quantum? Because quantum computing has a lot of potential in different areas, mainly because it offers algorithm speedups, because quantum algorithms are shorter, more efficient than classical algorithms. So they can be very helpful in security, drug discovery, optimization, logistics, and artificial intelligence. So we want to exploit this in fast gravitational wave detection. Quantum programs are not fully quantum, just the processing can include quantum stuff, but the data preprocessing and post-processing is classical. Machine learning algorithms can be fully quantum or a hybrid between classical and quantum bits. And we can optimize this classical quantum balance in order to get better results and to improve classical algorithms. So let's get to gravitational waves. We started with some proof of concept work where we simulated some gravitational waveforms using this simple model. It's a Newtonian model. And these are the waveforms which we simulated using an in-house MATLAB code. You can find it here. The only parameter that was varied was the source mass ratio. All the other parameters were fixed. And we simulated like 400 waveforms and split them into training data and testing data. Here are the plots of a waveform from each category. These are not physical sources, but for proving our idea, we use these waveform categories with very dramatic mass ratio. For classification, this kind of waveforms, we used the VQC, the variational quantum classifier, as QNN core, as the core of a quantum neural network. And it works as follows. First, we take the classical data and encode it into quantum data, which is then transformed by a quantum circuit and then measured. The measurement result has to reflect the class of the input state. So samples from one class are transformed in such a way that they group in an output class, and the same goes for the other class. And this routine is optimized such that the output is very well clustered in two classes. As models for our QNNs, we started from two simple tutorials. These tutorials use some specific Python libraries, specially designed for quantum computing, Penny Lane and Qiskit. So we'll call them the Penny Lane model and the Qiskit model. This is the diagram of the quantum neural networks workflow in the Pendeley model. So we start from the waveform features like standard deviation, minimum, maximum, quantiles, these signal processing features. We take only 4 of them and feed them to the quantum neural network. Each sample, each gravitational wave samples has one of these feature vectors, and they are used to compute specific quantum computer states that encode this classical information. And then these states are transformed using a parameterized circuit. The parameters are trained such that after measuring the state, the output reflects the class our sample came from. This is the circuit. First, we can see the feature map, which is the part that encodes the classical information into quantum information. The violet gates take as input features from the feature vector of each sample. And then we have the NZs, which is repeated 7 times, where our quantum neural network has 7 layers. And there are 6 parameters which can be trained in each NZ. And in the end, we measure and we optimize the NZ parameters until we reach decent accuracy. Well, our decent accuracy was 100%, which is great. Well, we can see in the right plot that the classes are very different, so the test was not so hard for the quantum neural network, but it proved its feasibility. Let's move to the Qiskit model, which is actually a hybrid quantum classical network, because the encoding of classical information in quantum information is done with a short multilayer perceptron followed by a single layer with a single quantum gate, and then measured, and everything is optimized. Here is the circuit. So the quantum circuit ingests only one number, which is the output of a short classical neural network. And after measurement, we optimize everything, meaning basically just this parameter of the violet gate. Again, we obtain 100% accuracy. All the waveforms were correctly classified, which demonstrates again that quantum neural networks, pure quantum or hybrid, are a good choice to classify gravitational waves data. Of course, we tried to run something on a real quantum computer. All the work was developed on simulators, on classical simulators, basically on our laptops. But there are available quantum computers, freely available actually, like the ones of IBM, and we tried to run the testing part of the quantum neural network on a few quantum computers, and for 100% ideal accuracy, we went down to even 30%. We tried different error mitigation techniques like live calibration of the quantum computer, like training the model using noise models of the quantum computer we run the program on, but nothing worked. So This result shows that quantum computers are still prone to errors and very reliable, but progress is made constantly. Okay, so this proof of concept work was published in a paper, which you can find here. And after we finished this, we could move to the real challenge, the Sangria LISA Data challenge, which features more realistic gravitational wave sources. And we approach this in two steps. First, we thought the quantum neural network recognized the Sangria blind dataset as a noisy wave. And then we upgraded the model to recognize the mergers in this noisy wave. This is the first step in data pre-processing, because we have 1 year of data. This is not enough for a neural network. So we chopped everything in order to obtain as many windows of data as possible. This red square indicates how we extract the samples from the dataset. All right, so each sample was classified as wave or as noise. First, we got 1800 windows which don't overlap. We got them from the trained dataset and from the blind dataset and from the noise dataset. And we compute the same signal features which are fed to a neural network that encodes them in quantum information. And an NZ is trained such that the classification is optimal. This is the quantum circuit, is larger than the previous circuits. We have 16 trainable parameters in each NZ layer. And we succeeded in teaching the quantum neural network to recognize the Sangria blind dataset as a noisy wave, giving the brain dataset as a noisy wave and the noise alone as noise. All right, time to move on, always moving on. The second step of our approach is to take this pre-trained model and upgrade it such that from the noisy waveform, it can extract the mergers. We cut the Sangria train and blind datasets differently. Now the windows overlap and they total 63,000 samples. But the features are the same. The model architecture is the same. And let's see what we got. We could identify 5 mergers out of 6. The last one to be identified is really, really small, and the quantum neural network wouldn't find it. It wouldn't understand that there is such a signal. But let's see how the quantum neural network did compared to a classical neural network, because our colleagues solved this metadata challenge. They identified all the 6 mergers using classical neural networks, particularly recurrent neural networks. So the classical neural network uses all 5 projections of signal, while the quantum neural network needs only one. The classical neural network uses one feature, while the quantum one uses more features, but the classical one needs a lot more data samples for training, like over 6 billion data samples, while the quantum one needed um, above 1,000. The classical neural network has a lot of parameters, 4 million parameters, while the quantum one uses only 64 parameters. The complexity of each neural network is linear. So we can conclude that the quantum neural network is a really compact model. It doesn't require a lot of parameters. It's very simple. It doesn't need a lot of data, which is a great advantage because we don't always have a lot of data. Well, with the disadvantage that the smallest of the signals was not detected. It was not detected yet because we plan to get inspired further from the classical approach and detect the last merger. We are working on different architectures like quantum long short memory neural networks, like quantum kernels, and even improved versions of the variational quantum classifier. And we are optimistic in this for this purpose. Thank you for listening to me, and if you have questions, I can answer you.
All right, thanks very much for the talk. So, any questions? Okay, maybe I can ask the first question. So if I understand correctly, the what you're doing right now with the quantum neural network is identifying events from the raw data.
Right.
But can you? I also in the beginning you were also classifying events into
Yeah.
groups. So can you also use the same algorithm uh, to classify a waveform as belonging to GR or something that's not GR?
I'm optimistic that we could do this. We didn't get to do this. We only classify events, like realistic events, in noise and signal, or signal and mergers, but we could work on classifying the sources. It's for future work, identifying parameters and so on.
Sure. But in principle, you could do that with the
Yeah,
quantum neural networks.
yeah.
This is very exciting. Thank you very much.
Thank you.